please.
Hello? Hello? Hello?
We can see you. We can hear you.
Do you hear me? So I can start, yeah?
Yes.
Yes, everything is fine.
Okay. All right. So thank you for the invitation. My goal is to talk about non-commutative cluster varieties and their Poisson and the like structures. But I would like to start first because it's a conference on isomonodromic deformations. I would like to connect a little bit with that. So I will start with some remarks of very general nature, which I'm sure most of you know, but still. So there's a general fact that if you have a G, which is a split semi-simple algebraic group over Q, for example, PGLN, and if you have a Riemann surface, sigma, with punctures, so it's a Riemann surface with punctures, and I assume it's of type S, this my topological surface, then there are two moduli spaces. One of them is so-called de Rham moduli space, which is related to this group G, Riemann surface sigma, and some type, irregularity type. So this is G bundles with meromorphic connections. On sigma with singularities at the punctures, and of some irregularity type, which is fixed, and I call it beta, something. And then this moduli space depends on a Riemann surface, of course, and it also depends on irregularity. And there is a whole big space, which is the moduli space, analog of the space NGN. And so this is some kind of wild moduli space. And what's important for us is that there is a fundamental group of the space. We can call this way, it's just pi one of this PG as beta. And this space, it incorporates the usual space MGN, but it's bigger and sometimes much bigger. And so that's one player on the one hand side. And then there is a Riemann-Hilbert correspondence, which says the following, that if you consider this space, and the Rham of G sigma beta, and as I said, it's fibered over the space P G S beta. But then there is another space, which is a topological space of topological space in Betty, G S beta. And this space is actually locally constant over the base. So there is a map here pi beta, and there is a map here pi de Rham. And so this is non-trivial deformation, as all of you know. It depends very much on the point on the base, but this one locally does not depend. And so there is a Riemann-Hilbert correspondence which identifies the complex points. And so if you fix some point here, then you get isomonodromic deformations. So that's what we're talking here. But there is also important fact that the group, the fundamental group of the moduli space acts on this space because it's this identification. I mean, the space is a locally constant variation, but if you go around, come back to the same point, you apply automorphism of the fundamental group. And so when we study isomonodromic deformations, you can say that we pick some point here and look what happens here. But also because there is an isomorphism, we very much use the fact that this space is Poisson. So that's another feature of this subject. And there is a general result about this called theorem. It has a long history. So it the whole subject, I mean, we did this with part of this with Laludefok, and then some other people. And then essential role plays our work with shame. And then the final kind of comments which make the statement which I'm going to make, you can find in the paper I'm talking about, this section 11.4 of 2108-04168. So this paper with Maxim, and the statement is that if you consider slightly bigger space at some framings, then this space has actually cluster Poisson structure. So it always has cluster Poisson structure. So it has equivariant with respect to the mapping group cluster Poisson structure. And why it's important for this meeting, I guess, because as explained, as I learned from several people, for example, from Bertola and Korotkin a few years ago, and I think Nikita Nekrasov also was explaining similar things, that actually it's important to compare. So when you talk about tau function, you compare two kinds of Poisson coordinate systems, Poisson or symplectic. One comes from the fact that this cluster, so it's one sort of this, and the other has another origin which relates to MDRAM. And so the only point I'm making in the beginning is that it's important to understand that this right-hand side has cluster Poisson structure. Now, what I'm going to do today, I'm going to give some kind of variation on this theme, and the idea is the following: that you can imagine that the group is GLN, but you want to take this GLN over some arbitrary R ring. So, for example, you can try to take R equals matrices over some big ring, over matrix ring of some size, or you can take R to be any non-commutative, I would say field, but kind of ring when you specify which elements you can invert is good enough. So basically, we're trying to understand what you see here in the situation where the group is GLN, but the coefficients are anything, any kind of commutative ring. And the claim is that nevertheless, we see all the same structures. We see cluster structure, cluster Poisson structure when it's there. It's variant which produces symplectic or presymplectic two forms. And so my goal is to explain this. And so my hope is that this may be relevant for the two things which I just mentioned, the isomorphism deformations and tau functions, but I'm not going to talk about them. I'm going just to talk about this feature of the small spaces, that they can be made non-commutative, keeping all the structures, and I want to explain how exactly this works. Okay, so after this introduction, I want to start first of all with basic example, which some of you may see in Maxim's lectures sometimes, years ago, maybe my lectures, but I'll spend maybe 5 minutes on this example and then proceed explaining what the basic structures it has. So this basic example is the following. So you take V to be vector space over this non-commutative R, and you suppose that the rank of V over this R is M, a given integer. Then you take a flag, so we want to consider flags. This means that we take vector space phi and filter it by subspaces. Every time we skip one dimension, we go one dimension less, so it's F0, F1, and so on, Fm, which is 0. And so it's a codimension of Fi is I. And you want to study, so the question is how to understand collections of flags in a vector space of a non-commutative field modulo the action of GLN. So you can say something like that. You want to consider configurations of some number of flags modulus the action. And we want to describe some cluster coordinates in this space. So let's do the first non-trivial example. Let's consider a situation when we have two flags. So let's start with the definition. Let's say that a pair of flags is generic if the following condition is true. So first of all, let's call this pair of flags A and B. This pair of flags is generic if the following is true. If you take a vector space and project it to quotient by A-dimensional subspace of first flag, you can also map it to the quotient by the B-dimensional subspace of the second flag. And if you assume here that A plus B equals to M, then we insist that this is isomorphism for any AB such that sum is M. That's generic flags. And then it's a very well-known fact that if you consider just generic pairs of flags in V, this is the same thing as decompositions of your vector space in the direct sum of one-dimensional subspaces. And in this decomposition, you can return back very easily. You just take the filtration which is induced looking from the left or from the right. This way you get the flag A, and this will get the flag B. And if you go from flags to decompositions, then you just write a formula that this LB equals intersection of A minus 1 with B minus 1. And then you get direct decomposition. So here you have to assume that A plus B is M plus 1. Okay, so it's statement is proved. Pair of generic flags is the same thing as decomposition's direct sum of one-dimensional subspaces. What about triples of flags? So first of all, we want to have a similar definition. We say that if you consider generic triples of flags in this vector space V. Sorry, I actually want to give you a definition, so I beg your pardon. Let's say the generic, sorry, proceed to theorem. By definition, generic triple, let's say A, B, C, means the following condition, that for any triple of numbers A, B, and C, which sum to M, we have a similar condition that V, which go into V mod A sub A, plus V divided by B sub B, plus V divided by C sub C, is actually isomorphism. So generic means that you have an isomorphism. And now the theorem. And this is a prototype of theorems about this moduli space of Stokes data. I forgot whether I said or not. So this space we called moduli space of Stokes data. And so that's a primary object. What I want to explain, I want to describe generic triples of flags, generic in the sense which I just mentioned. And the theorem is that there exists a canonical equivalence of groupoids. It means you can just say canonical bijection is a little less precise than what I'm writing. But you can go over there, which says that if you have generic triples of flags in V, this is the same thing as the following data. You want to consider line bundles, R line bundle. Remember, our base field is non-commutative. are like bundles with connection on a certain bipartite graph, which I draw in a second, and called gamma m. And so line bundles with connection on this graph are the same thing as triples of Flux. Now, how do you draw this graph? Let me do it. So you first of all start with a triangle, and then you mark some points. Some of them will be black, and some of them will be white. So this is the case when m equals to 4. And so you put m points, 4 points here, and then you start drawing white points this kind of way. It's a kind of inductive procedure which you see from what exactly I'm doing. And here it goes on my, beg your pardon, let me start over because it's kind of getting a little less nice than I want. So we have something like that. Okay, and then we keep growing like this. And so on. Okay, so I finished this drawing. So you want to consider the line bundles, but the line bundles are considered here. I can add, of course, the ends, but I do not add the triangle. So you consider line bundles on this graph. So the outside of the graph is not necessary. I mean, the outer triangle is not there, so you can just delete it if you want. Okay, now what does the theory mean? First of all, I'll prove it, but I also first of all want to explain what does it mean. So first of all, if your field, let's say the field of complex numbers, commutative, then the right-hand side is nothing else but a collection of numbers, non-zero numbers, and we take m minus 1 over 2 of them, because we can take monodromy around every hole here, and we get a number. So we have 3 holes here. Now, and this is precisely those cluster Poisson coordinates which we have in commutative case. But if we have R non-commutative, then the main takeaway from this is that there are no, we no longer have coordinates. So why we no longer have coordinates? Because we wanted to consider, for example, a circle, something like that we have inside of our graph. Topologically, it's a circle, but we have only monodromy of our local system, one-dimensional local system over the circle. It doesn't give you a number. So this kind of data is given by R star divided by the conjugation by elements R star. Like if you take matrices and by n matrices, then it's basically defined by n numbers instead of n squared. So you lose lots of information, but there is no coordinates. Nevertheless, this is the adequate language. So we have to talk about this local system. So we have to translate the usual setup of cluster Poisson varieties to the setting, and this can be done. And before I explain how this can be done, let me just explain how you construct this isomorphism. The construction is very simple. Both the constructions, the proof are very simple. So you notice that you have white vertices and black vertices. If you consider white vertices of gamma m, then there's the same thing as solutions in integers of the equation a plus b plus c equals m minus 2. And if you consider black vertices m minus 1, if you consider black vertices, this is solutions of the same equation equals m minus 2. And therefore, we can introduce the relevant spaces. One of them will be space L related to white vertex labeled by these triples of integers. And by definition, as for pair of flags, we just consider intersections of the corresponding subspaces indexed by those triple of numbers. But we also consider planes. So this was a line, L line. And now this will be a plane related to ABC, which sum to m minus 2, as you see here. And the plane is given by exactly the same formula. It's a plane just because we have different conditions, m minus 1 here and m minus 2 here. Now, what can we do with these lines and planes? We organize them in a diagram like that. So we have 3 lines, and they actually sit in the same plane. So this is my plane, PABC. And the lines, for example, this is A plus 1, BC, and so on. This is LA, B plus 1, C, and A, B, C plus 1. They all correspond to white vertices. So we get a diagram like that, and now we make the main definition for us, the second main definition. We say that let's just create the space L, which corresponds to the black point ABC, as a kernel of the natural map which you see here. You have the 3 L's, which you see on the diagram, and they embed to P. And so we take the kernel of this map, it's L. And so now we have lines corresponding to white vertices and the black vertices. And we just need to explain where is the connection. And so the connection comes in a natural way because this L A, B, C, black, it actually sits, it maps. It sits in the sum of 3 things, but it maps therefore to each of them. So you can go to L whites here, and we are done. So this is our line bandwidth connection. And it's also easy to prove that this is an isomorphism. So, okay, so this is cluster Poisson coordinates, but the problem is that there are coordinates, but there are no coordinates in the non-commutative world. However, things get better if you consider decorated flags. So what does mean decorated flag? This means that you have a flag F plus you have non-zero vector Fi in each of the quotients, Fi minus 1 divided by Fi. So it's a non-zero element as a quotient. And then we have an analog of the previous theorem, which describes equivalence. So there is canonical equivalence of groupoids between the following objects. On one hand side, we have generic triples of decorated flags. And on the other hand, we have almost the same, but not exactly the same. We have R line bundles with connection on the same graph gamma m. That's exactly what we had before, and that's not surprising because 3 decorated flags give 3 flags. But where are the decorations? The decorations are given by trivialization, so it's a plus trivialization on every zigzag path. So what is zigzag path? So on this graph, in general, zigzag passes just the passes on my bipartite graph. So it's a graph which you draw on a plane. So you can turn right at one kind of vertices and left on the other kind of vertices. And so this way you get this zigzag path. In this case, it's going to be something like that, although you might have many more edges here, it doesn't make any difference. So you just, this red line just goes, it turns left at white, right and black, and so on. And so on the graph which I was talking about, this trivial line graph, there are plenty of this this kind of zigzag passes. Namely, there are m parallel to each side. So, for example, one of them goes like that, then the other goes like that, the other goes like that, and so on. Here we have, I hope I didn't make a mistake or something. And then there are also the others which corresponds to the other sides. And so all I demand now is that not only I have a local system, but it's trivialized on each of these exact flags. And this brings us a big benefit, because now we can define the coordinates. So the key difference between the second kind of problem and the first one, that there exist canonical coordinates which are analogues, not exactly, but the analogues of the A coordinates. The only caveat that, as you'll see, the word coordinates is a little overused, but you will see this in a second. There are more numbers than dimension of the space. So how you define these coordinates? This is very, very easy, because you have an edge, and then you have two zigzags which go in the other way to each other. And so let's call this zigzag, let's say gamma 1, and this zigzag has gamma 2. But then they come with trivialization. So you have some section here of this line bundle and here, and you can compare them. So you can take section S gamma 1, and you can take section S gamma 2, and you can compare them at the point when they intersect. And then their ratio is given by some number, and this number depends, this number is invariant of the edge. So those delta E are the A coordinates. And the first thing is that we can calculate them. So there's a theorem that delta E are ratios of Gelfand-Rete quasi-determinants. And actually, this is a good way to understand what the quasi-determinants, because they appear very naturally. You don't have to invent them; they're just there, and their property is also immediately transparent from this picture. But as I said, the little caveat is that there are some relations which are obvious, but usually when we talk about coordinates, we don't want to have relations, but here it's inevitable. And the relations are the following. So if you have some vertex, then in our case we have three edges, and then this coordinates related to these three edges, when you look to them, let's say plotwise, the product is -1. Why -1? I don't want to actually explain why -1, because I need to talk then about these twisted configurations, but the sign has to be -1 if you do it correctly. But the most important thing is that there is a relation, it's a monomial relation. Forget about -1. And there are no more relations. Okay. So now we can, so this was an example, and what this example tells you is that if you have three decorated flags, then you can introduce some kind of coordinates. But then, as usual in cluster story, the main point is that you have not only that you have coordinates, but you have different ways of put these coordinates into your game, usually infinitely many of them, and you have to put the relations between them. And so let's see how this works in the non-commutative world. But before that, let me give you a definition in a more general setup. So let's suppose that gamma is a bipartite ribbon graph. any graph like that. And then we define the notion of A coordinates on this gamma as the following quantities. For each HE, we have a non-commutative number, non-zero non-commutative number, and then we have relations. So this corresponds to oriented H, I would say. So this H is oriented. And so what happens if you change the orientation? You just invert the number up to the sign. And also, if you have a vertex where you have many edges, like E1, E2, and so on, En, then the product of them, as before, equals to, again, -1. And then it's very easy to see, it's a kind of lemma, important but very easy, that this kind of numbers, A coordinates on gamma, they're in one-to-one correspondence with R line bundles with connections in the graph. Connections on gamma, and very important condition is that they're trivialized on each zigzag. So this way we get a definition of A coordinates for a given graph, and this plays a role of the cluster torus. Now the next question is, how do we glue? And so then we have this 2x2 moves. So it just means that you can take your graph and let's suppose that you have 4 black vertices here, and then the graph inside looks as this one. And you can have whatever you like outside. So here, whatever you like can happen. And then you just mutate it in a way that you keep the outside the same, but the inside changes. So the white vertices, they jump to different black vertices, but the outside situation is the same. So that's the standard moves. Now the question is, what happens with coordinates under these moves? And here is the answer. So as you remember, the coordinates are assigned to the edges. So we have here coordinates, and here we have B1, B2, B3, and B4. And then there are some formulas which tells you what's going on. The formulas are the following, that B1 equals 1 plus A3 inverse A3, and big A3, big I is just AI times AI plus 1 times and so on times AI plus 3. Because in this case you have 4 of them. We just start from I and go cyclically. And then the coordinate B2 is 1 plus A4, and so on. So then you apply just the cyclic permutation, because the diagram has cyclic symmetry of order 2. So I already wrote the formulas. It's very easy to see that these formulas are self-dual. If you do it once again, you get back. And also we have some little claims that there's a pentagon relation. They satisfy pentagon relation. And so after that, you can define what is cluster A variety. So cluster non-commutative, sorry, that's the key point.
Excuse me, please. Just I missed. What is big A?
Thank you. Let me write it again. It's a kind of monodromy. So let me just write it. A3 equals little a3, A4, A1.
It's a definition. Okay.
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 Let's see what we'll do. So then there is a non-commutative cluster variety, which is defined in the usual way. So you just glue all non-commutative cluster theory by transformations assigned to 2x2 moves. This is a Abel formula. And so then as many graphs which you have which are related to each other by these 2x2 moves, then as many Tori you have, you glue them, you get some kind of non-commutative object. There is some little extra things which you can do, and I want to pretend that I want to ignore them. So believe me, this is the essential thing. There are some other reductions you can do. I really don't care about this at the moment. But the interesting thing is that there is a symplectic geometry. So there is a non-commutative two-form omega. So it's just exactly like in the cluster story on the space which you can call A gamma. This non-commutative cluster variety A gamma, where you start with the bipartite graph gamma. And so to define this form, let me remind you a little bit of standard facts. Let me introduce a two-form of the following shape, which is dA, dB, B inverse, A inverse. And this means the following, that you actually can pretend that A goes to some n by n matrix A, and B is like some n by n matrix B, and then you want to consider 1 over n trace in matrices of differential of A, differential of B, B inverse, A inverse. So that's what this notation means in context of matrices, and you can formalize this if you want. But then there is a formula, there's a theorem. To formulate this, I assume for simplicity that gamma is a three-valent graph. There is also explicit formula in general, just don't want to spend time on this. And so the claim is that if you consider the following two form, which is just sum of what? So you have white vertices and you have black vertices. And if you have a white vertex, you have three numbers, A, B, C, and if you have black vertex, you also have three numbers. Let's call them A prime, B prime, C prime. And so you just write down the corresponding two forms. And the main theorem is that this two form is invariant under these transformations which we introduced before. So let me call them star. So this is a fact. So it has this non-commutative two form, and unfortunately, it's a difficult theorem. So I wish at that moment the theorem will be as obvious as everything else, but not yet. So it's proved by calculations and the lots of them. So now, what is the main property of this form? So first of all, it's invariant. Secondly, it's not exactly closed, but it's if you take its differential, then you get a sum over all external edges E of gamma of a certain three form. And this three form is very well known to everybody for a long time. This is just the standard A inverse dA cube form. For example, if you look at Chern-Simons or whatever, you always see this form, whatever part of science you belong, it's always there. And then the key property of this form is this identity, that if you consider this form and put it to the edges E1, E2, and E3, then again, it's well known that if you take the sum of these forms, E1 plus or minus, depending how you look at this, so this is actually exact differential. That's exactly a differential of this AB, which I related to these edges. So this form is well known, and the context in which I know them for edges is that when you calculate n-dimensional homology group of the space BG with coefficients in the complex of holomorphic form of degree bigger than n, then there is a Chern classes here, and you can write them down explicitly. And if you consider C2, then you get this component are just this and that. So this is just the second Chern class. So this data is precisely the second Chern class, but with coefficients in this kind of drum type of homology. Okay, but then the property is that it is invariant. So now let me give you an example where you see how this works. So let's do an example. In the case when we consider just gamma 2. It's not about forms, it's about the coordinates. So I promise that the coordinates are Gelfand-Raytak determinants. And in this case, it means precisely the following, that you have this nice bipartite graph. And then you have three flags. What does it mean you have three flags? In this case, when m equals 2, this means that this flex is a vector and another vector considered modulus of previous vector in this two-dimensional non-commutative space. And then you can encode these vectors. I need, for example, this triple A1, B1, and B2 by 2x3 matrix. This is like A11, A12, B11, B12, B21, B22. And then I claim that the coordinates which we assign by this procedure, if you unfold all the definitions, are precisely the following, that here stands the quasi-determinant, which I denote delta A1, B2. Here stands quasi-determinant delta of A2, B1. The rest is cyclic, except that there is little signs which you have to put in, which I want to ignore. But this delta of A1, B2, this is like vectors, A1, B2. This is, I emphasize, this is like vectors. So all this is like vectors of columns. And so this is delta related to pair of vectors. This is just, by definition, the following. So it's A11 minus A12, B12 inverse A11. Yes, I hope I'm not making a mistake. Multiplied by B21 minus B22, B12, B11 inverse. And this is in the notations which are used by Gelfand and Raytak. This is quasi-determinants of the following shape. It's 1, quasi-determinant multiplied by the inverse of this kind of 2-1 quasi-determinant. And I claim that absolutely the same happens for any configurations of flags, for decorated local system on surface, and so on and so far. You always get quasi-determinants, and you can write them down. And actually, writing them down basically boils down to the two-dimensional situation. But now, here, if I wanted to proceed from here to this non-commutative form, I would have to create a second triangle here to make another coordinates here, consider flip, and then change the triangulation. It's a usual game. So if you change triangulation from this one to this one, then those numbers, this is a non-commutative number, so all these numbers change somehow, but the output is that the two form is invariant. Okay. So from here, we can go to two directions. We can either go to Poisson structures or we can go to 3D. I would prefer to go to 3D because we still have coordinates in this case. So this kind of 3D in the A setup. And so what I wanted to do now is to discuss non-commutative cluster Lagrangians. Lagrangian means Lagrangians of variety, not a function. So the general situation is the following, that if you have some surface, maybe it has punctures, And then if you consider moduli space of this m-dimensional local systems on the surface with some decorations at punctures, then this space has a structure of non-commutative cluster A variety. And I basically told you the proof because what you do, you triangulate the surface, you put this standard construction on each triangle, and then you're done. But then you need to do flips of triangulations, and using this theorem, using this transformation formulas, you know how to proceed, and you also know that the two form is preserved. So in this case, we get the space, and the space comes with a two form. This two form is actually usually degenerate, but never mind. That's a two form. Now, what happens if we decide to put a threefold in the game? So what if we put here some threefold? So in a situation when we have M is a threefold, and the boundary of M is actually our original surface S, and it's with punctures, so you have to talk about this. So you put this little one-dimensional punch lines everywhere. So, okay, then the moral of the statement is the following, that if you consider the space, so we consider all m-dimensional decorated local systems on S, which can be extended inside to M. So that's the object to consider. And in the usual situation, this is a Lagrangian variety, which you get this way, so you can call L sub M, and which sits in our A M related to the boundary of M. And so this has two form. It's pre-symplectic, and this again I need little details because it's a two form which is slightly degenerate, but let me pretend it's like symplectic. So this is Lagrangian. So and what I want to do is, my goal is to have a theorem that the same is true in non-commutative case and better than that, plus that there are some explicit equations defining this L. So this is actually nice even in the case when it's commutative. Now let me explain how to do this. So in order to do this, I have to explain, I have to give you some device which produce you lots of Lagrangians varieties, which are non-commutative Lagrangians varieties, and actually this non-commutative cluster Lagrangians varieties. So I wanted to have lots of examples like that. And this setup, when you have threefold and surface on the boundary and consider connections which extend inside, this is a possibility, but it's better to do it in a more general setup. So what we want to have, what we wanted and what we'll have in a second, is a 3D analogues of bipartite graphs. And this 3D analogues of bipartite graphs, they deliver us the equations. They're actually not graphs, so let me give you a definition. So first of all, let me remind you a little bit of information which some of you know. So if you have a bipartite graph, then you assign to this bipartite graph, as we discussed, the zigzag passes. And then we can make out of them something which is called, which Dylan Thurston called triple crossing diagram. This is this triple crossing diagrams. It's a very nice and very elementary notion. The key point is that you have lines on the surfaces. These lines are oriented, and the orientations behave like that. So the only intersections are triple intersections, and the orientations are this way. Now we want to generalize this, so we can define 3D analog. So this was in 2D. In 3D, you can actually generalize this to any D, but in 3D, we're talking about a quadruple crossing diagram. For simplicity, let's say crossing diagram of co-oriented smooth surfaces in 3D manifold M. And there's the following data. So first of all, you have a collection of surfaces, which I just mentioned, which are smooth and co-oriented. And they satisfy the following conditions, that all intersection points are either the unavoidable intersections of two planes, like that. So it's this kind of intersection points, or the quadruple intersection points, or isolated. Of course, I don't have to say this, just the points, or quadruple intersections. And then there is an analog of this condition here. So this condition sounds as follows, that if you write conormals to them, then you have 4 conormal vectors, and 1, and 2, and 3, and 4, and certain linear combination of them with positive coefficients must be 0. There is, of course, one linear relation, but the condition is that the coefficients of these linear relations are strictly positive numbers. If this is the case, then we call it quadruple diagram. And it's obvious how to generalize this in n dimensions. Now, the key point now is the following, that I can associate. So if I have this Q diagram, let me still Q, which sits in M, then if you go to the boundary, then you have this cube diagram intersect with the boundary, which is, and this is an exercise, but an obvious exercise, this is a triple crossing diagram. And to triple crossing diagram, we can associate this non-commutative, let me call it T on DM. We can associate this cluster variety, non-commutative cluster variety, related to this object. And we wanted to have here a Lagrangian subvariety, which corresponds to this quadruple point diagram. And I'm going to, there are several ways how you can proceed. I can define it in terms of sheaves, but I would prefer to give you a construction which is a calculation of this subvariety. So I'll give you a formula how we define the subvarieties. Here's how it goes. So if you have quadruple diagram, then you can fix one of the planes, and then the other planes, they form you, then you see something like that. The other planes, they intersect, and at this point, you see that you have 3 other planes. And then I want to assign, so then I have something which is called singularity graph. Let's call graph of this Q, and it has these edges, and it has vertices which are quadruple intersections. So it looks like that. And so we assign to each edge E of this singularity graph a certain number, non-commutative number in R star. And then we demand that when you see these 3 numbers here, like A, B, and C, Then we demand that A, B, C equals to 1. And also the same is true, of course, on the other side. It's maybe just so that you remember that we have the other side of this plane. So there is some picture here. And then there are similar coordinates here. There is a similar condition. This means that each cone like this produces a monomial relation between these coordinates. But then look what happens when you have a plane or a surface here. Then quadruple point diagram means that you see here something like that. So if you see triple crossing, and that's what happens. So if you look this particular plane and draw it here, let's call plane pi, and it's just here. Then the other planes give you this triple cross intersection, and then you put here, there are some numbers here, let's call them Z1, Z2, Z3, Z4, Z5, and Z6. And then there are the following equations. First of all, if you put Z1, Z4 multiplied by Z5, Z2 multiplied by Z3, Z6, this equals this minus 1, so it's minus 1 here. That's a kind of trivial equation, but the interesting equations are the following. You put Z1, Z4 plus Z5, Z2 inverse plus 1 equal to 0, and then cyclic shift of this. Cyclic means that you put C5, C2 plus Z3, Z6 inverse plus 1 equals to 0, and Z3, Z6 plus Z1, Z4 inverse plus 1 equal to 0. And it turns out that all these equations are equivalent. Just one of them is enough. If you have monomial one of them is enough. And so that's it. So, so the claim is that this LQ is defined by these equations. So this means that if you have arbitrary quadruple diagram, which somehow sits in a threefold, and so you put it somehow inside, I will try to draw it. So on the surface, you see the triple point diagrams, but then you have lots of equations, you have lots of coordinates related to this edges of the singularity graph, and you have lots of relations which are local in nature. So all relations are local, meaning that they are written in the neighborhood of this point. And if you put this z coordinates inside and then a coordinates outside, then you get a system of equations and the z inside. And if you can solve them, so you can solve them, and then you get Lagrangians of variety in a's inside. So the main theorem is that it's actually isotropic, and the fact that it's isotropic is actually equivalent to the fact, reduces to the fact that 2 by 2 move preserves the form, the 2 form. And so that's about it. So we draw the system of equations which defines this Lagrangians of varieties. Now, what do you do in practice? So let's suppose that you have a practical question. Let's suppose that you have a surface as before, S, and you want to consider this m-dimensional local systems. And let's suppose that we have this threefold sitting here. That what you do, first of all, there are some punctures here. You triangulate M, which induces triangulation, ideal triangulation of the boundary of M. And then you do, I don't have time, I don't have neither time nor what's important. Unfortunately, my computer will die and I stupidly bring things which will prevent it. But so I'm not going to explain how, but whenever you have a tetrahedral this triangulation, you can introduce some quadruple diagram with this tetrahedral T. You can construct some quadruple intersection diagram corresponding to this, and then they glue together. And so when you glue all them together for the decomposition of the triple on this tetrahedra, you'll get a big Q diagram, quadruple crossing diagram. And this quadruple diagram, as I just explained, produces a system of non-commutative equations, which gives this non-commutative subvariety. And so this is the way how you practically construct the subvariety here. I think I should stop here. It's just 1 hour. So thank you.
Thank you very much. Are there any questions?
I have a question. Is there Laurent property and positivity also in these non-commutative cluster varieties?
Yes. If you look at these formulas, you see that the signs are plus. Yes.
Okay.
But if you want, as usual, if you want to do this for the graphs related to configurations of decorated flags, you have to take not decorated flags, but what we call is already twisted decorated flags. This means that they are related in a circle, and when you rotate them, the last flag is multiplied by -1 to degree m-1, where m is the rank of the matrix. Then all signs are plus, and we have plus recording system. So yes.
I had a second question. Does this reduce to the Berenstein-Retak
Yeah, I should. Sorry. It's mea culpa. So absolutely. So when n equals 2, we recover. I beg your pardon. We recover Berenstein Retak. What's it called? Surface cluster algebras. Exactly. And so we give, I mean, they introduce the surface cluster algebras by saying that there are some variables, satisfy some relations, some rules obeyed. So from what we did, it follows that you can just solve these equations by writing down these quasi-determinants, but you get the same object. And actually, this whole work started in HES way, actually, right now, when we was 11 years ago, and so I talked to Berenstein and Retak, and so was trying to suggest that what they are doing in their cluster surface algebras has geometric meaning, and so this is just the output of this kind of geometric approach. So absolutely, so this delivers Berenstein Retak surface cluster algebras. Absolutely, when n equals 2.
Thank you.
Excuse me, please, I'm a little bit lost about what are these variables z. Maybe you could say a few words.
The variable z is a formal variable. I'm just saying that if you consider this quadruple point diagram like this, then the variables z they live on the edges. So on each edge of the, and remember that when you have quadruple point diagram, there are two conditions. One of them says that your singularities are either lines or singular points. And so if they're lines, they form a graph because there are singular points which they separate. And the point is that those variables z are attached to the edges of the singularity graph. Okay?
I see. Okay. Okay, fine.
Now, these variables z are not a free variables. They satisfy some relations. And the relations I explained. So I said that if you have this picture, if you fix one of the planes, this one, then and you fix a quadruple intersection point, then you see that you have a little tetrahedra, 3 surfaces which come to this point, and they therefore provide you 3 edges. And so the product of these coordinates equals to 1. The same happens here. This is one sort of monomial relations, but there is some other sort of monomial relations which you also see here. If you take a concrete plane, then you see 6 z's, and their product is 1. So these are monomial relations, and the less interesting the relations, but the really interesting relation is this one. So the claim is that you have these relations, and these relations, I claim, they're just equivalent, those relations, they're just equivalent to the cluster relations, to the change of coordinates. These two sets of equations are entirely equivalent. The only point is that when you look at this system of equations, it's dramatically non-symmetric, because there is no 3D, I mean, you imagine that you have 3D picture, but they're written in such a way which is grammatically not symmetric. And it turns out that it's possible to write them down in the way which is manifestly symmetric, because this one is manifestly symmetric. And so this is the point, that you can write the equations which define Lagrangian in such a way that you can rotate this tetrahedra where you can rotate around this quadruple intersection point, and it looks absolutely the same. And the very fact that it's really symmetry, you look at this way: go Z1 to Z4, then you jump to Z5 and go to Z2, and then you jump to Z3 and you go to Z1. So if you do this process, you will see that you get precisely 1, 4, 5, 2, which looks different orders, then 3, 6, and then will be again 1, 4, and so on. So this picture, cyclic picture, incorporates all the geometry here. And also here you have 1, 4, 5, 2, 3, 6, looks strange, but this red picture explains what's going on. And there is a theorem behind this. It's actually key theorem. The key theorem is that this condition can appear as a calculation of something. So we put some sheaves with one-dimensional non-commutative microlocal support in 3D, and then they have singularity at this quadruple point. And the condition that they have no wave front outside the four vectors which are normals to this plane is precisely this condition. So it's a theorem behind this. This condition appears as a condition that some sheaf, DG sheaf, which we're talking about, in 3D doesn't have microlocal support or except at the place where it must have in 4 directions.
Sasha, I have a question. The picture of Stokes data you
presented. Just a second, let me make sure that I will not disappear. This means that I will plug it out. Just a second. Yeah. Go ahead.
So the Stokes data you are discussing, non-commutative, and the structure corresponds to polar for the 2 of your local system.
No. It corresponds to, so the claim is that whenever you have arbitrary Stokes data with whatever type of singularity or the n, whatever type of degenerations, it always can be described this way.
Okay. And what is this symplectic form or whatever in case of commutative data, when you have a usual Stokes data for a linear system with singularities?
It's a little long story. I mean, first of all, it's small. Secondly, it's given by a braid, and unfortunately, I cannot connect my laptop back, so I cannot draw pictures any longer. But you have singularity points, and around the singularity points, you have arbitrary braids going around. And there is some data, it's a little complicated. So you have to consider this formal solutions in Piazza series, and you have to draw the corresponding curve, and then you have to consider some conditions on sections of your section. You consider space of solutions which form local system, but at this point is going to have some collection of flags which are recovered from the braid which you get from the formal solution. And then you consider all possible data like that. And this beta just tells you what kind of flag which you consider there. And then the claim that for whatever beta you put, it has cluster Poisson variety structure. And if you are in GLN case, it has cluster non-commutative structure.
Okay. Can you recover, once I wrote the symplectic form for Stokes data of arbitrary, is it encoded here somehow?
Yes, definitely. Otherwise, I would not write this to form at all. So I have again to formulate this more precisely because the modular space of Stokes data is Poisson. It's not symplectic and not presymplectic. And I can make a definition of what is non-commutative cluster Poisson variety, and then the statement is that it's non-commutative cluster Poisson. But I didn't talk about this. So if I want to talk about these two forms and coordinates, I have to introduce some kind of little extra data, which is called decoration near the punctures. And then it will be not all modular space of Stokes data, but a certain part of it, some subvariety. And on this variety will precisely have the structure of this non-commutative cluster Poisson space. And the two form will be there. And in the commutative case, it will be exactly the two form we care about.
Okay.
So somehow the statement is that when you consider the situation when you have n-dimensional local systems where n is like 3 times n. 3 is a given number and n is variable. You can write formulas in such a way that you think about 3-dimensional local system, but with non-commutative coefficients in terms of with coefficients is this n by n matrices. And this is a statement that the symplectic form related to the 3 n-dimensional differential equations, flat connections, is so universal that you can write it down in a way which remembers about this 3 times n data. So it's a certain statement about how you can write down this symplectic form and just express the fact that you can do this universal with respect to those n by n matrices.
Okay.
I hope.
Thank you. I understand what you are saying.
I think maybe we have more questions, but I suggest to stop in order to have 5-minute breaks before the next talk. So thank you again. It was a nice lecture.
Thank you.